In Chapter 6, Section 2, we're going to start talking about bisectors of triangles. And again, when we talk about bisectors and triangles, we're talking about perpendicular bisectors, and we're talking about angle bisectors. Before we start with the bisectors, we need to talk about some basic vocab terms that you might have not heard before. And one vocabulary term is concurrent lines. And concurrent lines are three or more lines, rays, or segments that intersect in the same point. So the kicker there is that whether it's a ray, a line, a segment, that's all irrelevant. It doesn't matter which of the three it is. It just means that they, you might have a ray, and then you have a segment, and you have a line that's infinite. But either way, they all meet at the same point. And so they would be concurrent lines or segments or rays. Now, that location where they meet, that's called the point of concurrency. Okay, so it's the point of intersection of the concurrent lines, rays, or segments. Okay, so not only do we have to learn the word, what concurrent lines means and what point of concurrency means, but we also give the point of concurrency a different name, sometimes depending upon how the point of concurrency came about. And so that's where this first part here, the circumcenter, comes into play. So the circumcenter is the point of concurrency. Notice it's a point of concurrency. So it's the name given to the point of concurrency of three perpendicular bisectors of a triangle. And that's the most important part here, is that the circumcenter, comes from perpendicular bisectors. And so again, let's look at this triangle. Don't worry about the circle yet. We'll talk about that after. But we're talking about this black triangle right here, okay? And if you notice, the red lines are the perpendicular bisectors of those sides of the right triangle. Notice that, for example, right here, we've got this is the midpoint of, let's call this A, B, and C. So this dot right here is the midpoint of segment AC. And if I draw a perpendicular line through it, it looks like that. Then BC has a midpoint here, this red dot that I'm drawing to the right, and its perpendicular bisector looks something like that. And the third side of the triangle has a midpoint as well, and here's the line that goes through that. And what you notice is when you draw those three perpendicular bisectors, they're going to meet somewhere here inside this particular triangle. That point right there, yes, it's the point of concurrency, but because it was created by perpendicular bisectors, we call it the circumcenter. Now notice in this particular triangle, the circumcenter is located inside the triangle. Well, if we go to the next shape over here, the next triangle, notice this is a right triangle. And again, we draw our perpendicular bisectors to all three sides, and you're going to notice that your point of concurrency, your circumcenter, is going to be on the triangle. And that's true for all right angles. And then the last one, again, you're going to have, this obtuse triangle here. And when we draw all of our perpendicular bisectors, you're going to see that your circumcenter is outside the triangle. And that's true for all obtuse. So again, acute triangles, the circumcenter is inside. For the right triangle, it's on the triangle, and for the obtuse triangle, it is outside of the triangle. And then the last thing here in the notes is talking about the circle. Notice how you have that blue circle, and again, let me just kind of erase everything else, right? And when you have that blue circle, you're going to see that the circumcenter is the center of that circle. Okay, so it's going to be the center of the circle, and the circle is said to be circumscribed about the triangle. It's around the triangle. And so, again, think of if the circle is around or the circle is circumscribed about the triangle, that would explain why the center is called the circumcenter, okay? So circumscribed, and then we focus on the circum part of it and circumcentered. Now that we know what a circumcenter is and how it's sort of created, right? We know the definition of it. We know how to identify it. Now we're going to learn to apply it. We're going to apply something with it using the circumcenter theorem, okay? And the circumcenter theorem basically tells you that the circumcenter of a triangle is equidistant from the vertices of the triangle. So again, let's look at this picture and kind of identify what's been given to us. And if you notice, what they did in this picture is they drew the perpendicular bisectors, basically D to P, F to P, and E to P. These are my perpendicular bisectors. Because they're my perpendicular bisectors, where they meet, again, is the circumcenter, okay? Now, what the theorem says is that if P is the circumcenter, then the distance from P to B is going to be congruent with the distance from P to A, which is going to be congruent with the distance from P to C. So PB, PB, PA, and PC are all congruent segments. And that's how we apply the circumcenter theorem. So now we're going to complete one of the types of questions that you might get related to circumcenter. So one thing we might ask you to do is just to actually identify the coordinates of the circumcenter. So again, to do that, you have to first draw the triangle, right? So we're going to start by drawing our triangle. The vertices are 0, 3, that's point A, 0, negative 1, that's point B, and 6, negative 1, that's point C. So again, I'm going to come in here and I'm going to draw my triangle. Now, what I have to do at this point is I have to draw the perpendicular bisector of each side. Thankfully, this is a right triangle. I know my circumcenter is going to be on the triangle, but when I have a vertical or a horizontal line, it makes drawing the perpendicular bisector much easier. So I'm going to look at line segment AB, and I know the midpoint of AB is at 0, 1. Now, again, I can use the midpoint formula like I've shown you in class, but in reality, you don't need it. I know that a line that is perpendicular to AB is going to be a horizontal line, so it's going to look like this. So that's the perpendicular bisector of AB. Now I'm going to do the same thing for CB or BC. I know the center or the midpoint of BC is going to be at 3, negative 1, and I know that the perpendicular line to a horizontal line is a vertical line. And so that is the perpendicular bisector. Now, at this point, I think that you already see where these two lines intersect. Well, guess what? That's going to be the circumcenter right there, okay? No doubt about that. It's on the triangle, and it's definitely going to be the circumcenter, and the coordinates for it is 3, 1. That's the ordered pair. So I know the answer here is 3, 1. However, you might because remember, it's the point of intersection for all three lines. And, somebody might ask you to write the third line, the third perpendicular bisector. Well, that one's not as easy because obviously AC is a diagonal line. But remember that I already know where it's at. So I know this is the midpoint of AC. So I don't have to use the midpoint formula to find the midpoint. Only thing I have to do is find the slope of AC. The slope of segment AC is going to be, again, I can do it mathematically or I can count. If I do it mathematically, I know it's going to be 3 minus negative 1 over 0 minus 6. I'm going to get 4 over negative 6 or negative 2/3. So that means the slope of the perpendicular bisector is going to be the opposite reciprocal of negative 2/3. So it's going to be positive 3 over 2. So if the slope is 3 over 2, then I can come in here and from that midpoint that I already know is one of the points, the circumcenter, I can go up 3 and 2 over, or I can go down 3 and 2 back, and I can definitely draw the perpendicular bisector, should I have to do all three. But either way, the circumcenter was already identified prior to that. Now that we understand circumcenter, we're going to talk about incenter, which is, again, another term for the point of concurrency. But this time, the incenter is the name we give the point of concurrency created by three angle bisectors of a triangle. So again, I'll get to the rest later, but I look at this triangle here, this black triangle, and I see that we have three angle bisectors that kind of went through it. We've got this one up here. Let me do it in a different color. Let me do it in black. We've got this line here. Notice it broke this angle into two congruent parts, meaning it's a bisector. We've got this line. Notice it split the angle again into two congruent parts. And we have this third segment, which broke this third angle into congruent parts. So those three things came together at this point. So this is the point of concurrency of this triangle, but we call it the incenter because it came from angle bisectors and not perpendicular bisectors. So what's different about an incenter? Well, again, first of all, what's different is how it's created. It comes from angle bisectors. The second thing is interesting is it always lies in the inside of the triangle, whereas the circumcenter is on the inside for an acute angle or acute triangle. The incenter is on the inside for every kind of triangle, acute, right, or obtuse, okay? And again, how does it get the whole incenter versus circumcenter name? Well, again, if you look at the circle is said to be inscribed within the triangle. And so again, the incenter is the center of that circle, but since the circle is inscribed, we call it incenter. So now that we know what the incenter is, how to identify it, we're going to learn the incenter theorem, which is really the application of what do we do with an incenter? What do we know? And it says here that the incenter of a triangle is equidistant from the sides of a triangle. So again, let's think of what we've been given here. Let's look at this picture. And we see that, or we're told that AP, whoops, no, I don't want to do that. We're told that line AP, BP, and CP are all angle bisectors, and they meet at point P. Well, point P is the incenter then, okay? Because again, it's created by the intersection or the point of concurrency of angle bisectors. And so what the theorem now tells us, the theorem says, well, now that we know that point P is the incenter, we know that the length from P to AB, which is PD, is going to be the same as PE, which is going to be the same as PF. In other words, this line here is going to be congruent to this line, which is congruent to this one, because they're all equidistant from the incenter to the line or to the side of the triangle. Now, we know that when we draw this line, it has to be a right angle. It has to be at a perpendicular line because that's the shortest distance from the point to the side, and that's the true length or distance of that point to that line. So again, that's the incenter, and now again, let's go to some problems or a problem using the incenter, Okay, so now we come over to this problem, and again, before I even start it, I need to look because there's a lot going on in that triangle. And I want to understand what it is that's happening. So when I look at this triangle, I recognize that this line from B to N bisected this angle. So I know this line is an angle bisector, as is AN, as is CN. And so I notice that point N is the point of concurrency of these three angle bisectors. So I know it's the incenter, okay? And once I know that point N is the incenter, then once again, I know that NE and ND and NF, which is the distance from the incenter to the sides of the triangle, well, that's going to be congruent. So these three sides are congruent. So ND, oh my gosh, what did I just type there? ND is going to be congruent to NE, which is going to be congruent to NF. And so if I go back to the beginning of the problem, it says in the figure shown, ND is equal to 5x minus 1. And NE is equal to 2x plus 11. Well, I can set these equal to each other because I know that all three segments equal the same thing. And if I do the math, I'm going to be able now to solve for my missing variable. I'm going to add 1. I get 3x equals 12, and 12, or x equals 4. And again, now, if x was 4 was the only part that I needed, or the question, I would be done. But I don't. What I need to know and what it's asking me is NF. Well, I don't have an expression for NF, but I have an expression for ND, and it's 5x, or 5 times 4 minus 1, and I know that's 19. I can double check because I have an expression for NE, and that's 8 plus 11, or 19 as well. So guess what? NF is the same as ND and NE. It's also 19. And so that's the work you have to do here using the incenter theorem, applying it. The second question says, can NG be equal to 18? Explain your reasoning. So it's asking me if this blue line right here can be 18. Well, this black line, NF, is equal to 19. The shortest distance from a point to a line is a perpendicular line. So this 19 is the shortest possible length. So therefore, I know that NG is not possible. It cannot equal 18, okay? Because it can't be less than the shortest side. All the other sides, all the other segments rather, from N to this side, any other ones I draw are always going to be greater than the 19 that I found. And so it's no. NG is going to be greater than 19, okay? I don't know what it's going to be, but I know it's going to be greater. So again, guys, this is really it for this lesson. You're going to have to memorize these things. You're going to have to memorize what circumcenter means. You're going to have to memorize what types of bisectors create it. We know it's perpendicular bisectors. And then we're going to have to know how to utilize the theorem and apply it and figure out what do we know from that. And same thing goes with incenter.